we know then about electromagnetic radiation. At least we know that we can have sinusoidal radiation. We'll come back to that later in next week. How do we get it started in the first place? So we know it can exist, but the question we want to deal with today is, where does it come from? And the answer has to do with charges, because we know charges create electric and magnetic fields. So if you have a charge, and the charge is just sitting there, it's going to make what? Electric fields. Okay, so we know a charge produces electric fields. If the charge is moving, so we say q times the velocity. If we have a moving charge, that makes what? Electric and magnetic fields, right? It doesn't stop making electric fields just because it moves. But we also have B, right? So we know how to calculate those things. Well, the new wrinkle now is that not just having a charge, not just the fact that the charge is moving, but the charge has to actually accelerate. That means the velocity has to change. Accelerated charges produce radiative electric and magnetic fields. Okay? And there is a particular pattern to this radiation due to a charge. And let's show a little demo here. Okay, what did I just draw? That's a positive charge. So what did I just draw here? Electric field. Now, what about those? There's something about those arrows, though. Those arrows are not getting smaller. So I didn't draw the magnitudes, but I've drawn directions. Okay, so you can think of these as unit vectors, right? They're just the directions of the electric field, just the pure Coulomb electric field, the first electric field that we dealt with at the beginning of the semester. And we know that the Coulomb field points away from positive charges. So I have a series of observation locations all kind of lined up in a circular pattern, and at each observation location I place an arrow in the direction of the electric field. And at the tip of that arrow I have another observation location. I draw the next unit vector in the direction of E, and I keep doing that sort of tip to tail. And I sort of connect the arrows, right? So I can think about, if I connect all these arrows together, then I can think of the pattern as being just a series of lines. And all the lines are radially away from the positive charge. And these are called, not surprisingly, electric field lines. Okay? So instead of field vectors, we could represent the electric field as just lines oriented away from a positive charge. And the field line representation we haven't really dealt with at all this semester. We focused on vectors at a particular location in space. But in upper division or higher, more abstract applications, the field line picture is often more often used for electric fields. So it's useful to know what it is. Well, that's the pattern for a static charge. Well, it turns out if you have an accelerated charge, this field line picture changes in kind of an interesting way. So let me run another program. And the field line's all radially away from the positive charge. And I'm going to accelerate the charge. I'm going to take a hammer and smack it. Okay? It's going to exert a small force for a short amount of time, but there's going to be an acceleration, right? Because it's starting it from rest, and if I hit it, it's going to have a speed. And so it's going from v equals 0 to v not equals 0. So for some very brief amount of time, there's an acceleration. So here I go. I smack the charge. And something happens in this field line picture. We have sort of a bend or a kink in the field line that propagates outward from the original location of the charge. And this pinkish sphere here is where the charge was, where it started. And the charge is now moving at a constant velocity downward. And let me restart the picture. So I smacked it. It accelerated for a shorter period of time. And when it accelerated, it caused this kink in the field line to propagate outward. Well, how fast do you suppose this bend or kink is moving outward? Speed of light. That's the radiation. This bend or kink in the field line is what we consider to be the radiative component of the electric field. And once you have a charge accelerate, then it starts to radiate. And the radiation or the direction of that field vector, or that direction of that radiative field, has a relationship to the acceleration. And I don't know if you can see this. Let me try this one more time. You notice that that bend in the field line changes size depending on what angle you're at. Okay, so right here we have a pretty large bend in the field line. As we move downward here, that bend, that kink, starts to get smaller, and in fact, in the direction of acceleration, there's no bend at all. Okay, and in fact, in the opposite direction of the acceleration, there's no bend at all either. So this radiative component to the electric field propagates outward from an accelerated charge, except in the direction or along the line of the acceleration. The radiative field is zero along those directions. We still have the Coulomb field. We still have the field just due to the presence of the charge, but we also have, in addition, this radiative field. Let's start again. So let me pause it here. Let's say I'm standing here, and I'm measuring the electric field at this location. What electric field am I measuring? The original field that was created when the charge was static, when it was at the original location. To me, it looks like the charge hasn't moved yet, because the information about the moving charge propagates outward at the speed of light. Okay? So I'm standing here. Now, of course, light, we've slowed it down tremendously here, but for some brief amount of time, I'm detecting the field before the charge even moved. And then, sometime later, I say, okay, there's my observation location, and now suddenly I detect this radiative field, and I say, oh, okay, now I see the charge is accelerated, and now I'm detecting the field of, again, it's the field due to the moving charge, okay? So information about changes or in the electric field propagate outward at the speed of light, and that information is, again, what we call radiation or light, okay? So we get radiation, but that radiation travels at a finite speed, and so we have to keep that in mind when we're calculating it. So what we're going to do is try to figure out, or at least examine the direction of the radiation or the radiative component of the electric field due to an accelerated charge. So I'm just going to give you a formula. It's not something you have to memorize, but it is something we're going to have to figure out how to interpret. And the radiative field, the radiative component, or this kink in the field lines, is given by the formula 1 over 4 pi epsilon 0, so the old constant again. It's going to be times a negative sign, q, times the acceleration vector perpendicular. So it's the perpendicular component of the acceleration, which we'll talk about what that means in just a second. But it's a perpendicular vector, divided by c squared, c being the speed of light, times r, magnitude of r. And it's not r squared, it's just r. Okay, it's just a 1 over r dependence. So the field is actually going to get smaller with distance. This radiative field is actually going to go down with distance, but at a lower rate, essentially. It drops off with distance only as 1 over r, not at 1 over r squared, like the Coulomb field. So what we want to think about is how to use this formula to get the direction of the radiative electric field. And we just have to go through some steps in order to do this, because we have to be careful about the geometry here. So here are the steps. Finding direction of E radiative. Step 1. Draw R. Well, R is what? What's the vector R again? Way back when we started calculating electric fields. Points from where? From the source to the observation location. Okay, so R points, as usual, from the source to the observation location. Okay? And notice also, if we're talking about, let's say I have an observation location here, right? Well, R is pointing from the source to the observation location, so R is pointing to the right. And I let this go forward in time. What direction is the radiation traveling when I'm looking here at this point? From my point of view, it's coming at me, so it's moving to the right. Okay? And if I were down here, the radiation would be pointing that way, right? Or traveling that way. If I were down here, the radiation would be traveling that way. So that is, if we know R, we also get the direction of propagation. So direction of R is the direction of propagation. It's just what way the radiation is traveling. Step 2. Draw an axis through the charge that is perpendicular to R, okay? In the plane of R and A, okay? But it should be pretty obvious from our applications. Find the component of the acceleration along the perpendicular axis. And that's what we mean by this A subperpendicular vector. And then finally, the direction of this radiative electric field is negative Q times A perpendicular. And where that comes from is, if you look at this formula, we have a vector equation. We're doing scalar multiplication on a vector. So here's the vector, right? That thing is positive. That's not going to change anything. This thing is positive. This thing is positive. But we have a negative sign and we have a charge that could be positive or negative. So we need to think about negative Q times A perpendicular in order to get the direction of the vector. Okay? If we have that, we know the radiative electric field is pointing in the same direction. Okay? So let's try it. Let's try an example. So here's an example. Here's a proton. We're going to do the same thing. Give it a smack or give it a brief pulse of an electric field that causes it to accelerate in this direction. And we have two observation locations. I'm just going to focus on observation location P here, which is directly above the proton. Let's just do step 1. What's the direction of propagation of radiation reaching up the observation location P? So we're not worried about the radiative field yet. We're just thinking about what direction is the radiation coming from. Okay, 60% of us say direction number 1, but there's quite a bit of noise everywhere else. Okay, so we should talk about this. A lot of people, I think, this is a question that kind of causes confusion every time I ask it. And I think the issue is that you're making it more complicated. It's simpler than meets the eye. It's less complicated than you might think. We're just talking about R. We're just drawing the R vector, right? Because we know that radiation coming from a charge down here, accelerating in that direction, and moving to location P would move upward, right? So if I draw the R vector, that's the direction of propagation. Done. Okay? From the source to the observation location is the direction of propagation. Okay? Questions? Okay? Just R. Just R. That's it. So if you can draw a vector from charge to observation location, you've got it. Okay. Given that, well, let's do step 2 first. We've drawn R. Now step 2 is draw an axis through the charge that's perpendicular to R. So I draw an axis through the charge, and that axis is perpendicular to R. So I'm going to call that the perpendicular axis. There it is. Okay. So I've had that axis. I now want to think about the perpendicular component of the acceleration. So what direction is that going to be? It's got to be 3. It's got to be 3. We're just finding the components of that vector, right? So you can think of it as like an axis. You have a y-axis and an x-axis. Well, in this case, you have a r-axis and a perpendicular axis, right? And we're looking for the perpendicular component. So I can break this vector up into 2 components. One is in the direction, one component in the direction of r, or call it parallel to r, and the other one perpendicular to r. So that is a perpendicular, okay? So it's just decomposing vectors once you have the axes, and that's got to be the direction of a perpendicular, right? Questions? Are we okay? Yeah, question. If it were an, okay, so let's talk about it. If it were an electron accelerating in this direction, that doesn't change a perpendicular because it's still accelerating in that direction. Okay, let's ask the next question, then we'll come back to that. Now I don't actually have a printout of this question, so let's just ask it here. Delete that. Oops. And say, what's the direction of irradiative when it reaches point P? Okay, and so it's not going to get there instantly. It takes some time to get there, but when it reaches point P, what's going to be the direction of the radiative electric field? So it's going to be direction 7. Direction 7. Why 7? There's a negative sign, right? So we have a negative sign times Q. What's the sign of Q? It's positive. Negative times positive. We have a negative sign multiplying this A perpendicular. So we get a vector direction that is opposite to A perpendicular in this case. So we get a electric field pointing in that direction. Okay, so let's back to the question of what if it were an electron? What if it were an electron? It'd be in the direction of A perpendicular, right? Because you'd have a negative times a negative giving you a positive multiplying A perpendicular. The electric field would be in the same direction. Okay. Now again, you have to remember that this is not occurring instantly. It takes some time. So if I know this distance is r. When am I going to, at what time after, and it starts to accelerate at t equals 0, at what time am I going to detect the radiation reaching me? How do I calculate it? The radiation is propagating at what speed? Speed of light, okay? So if the distance is r, that's going to be equal to what times t? C. Okay, distance or speed times time, right? Okay, so I can figure out the time. It's going to I'm going to detect it at distance or at time r over c, right? Okay, so so again, it takes finite time for the radiation to reach us, but once it reaches us, we can determine the direction using this method. Try another one. Let's try another one before we do a quiz. Okay, here's one. This is interesting. What is the direction of A perpendicular if we're looking at location S? We're looking at location S. A is pointing directly towards S. What's A perpendicular? Okay, 2 popular answers here. We have 4 and we have 9. Okay, so it's either pointing down and to the right or it's 0. Well, let's go through the steps. You have S over here, right? Okay, so let me erase some of this. So that's A. I draw my R vector. That points that way. And I draw a perpendicular axis this way. Can I have a perpendicular component? No. It's entirely on the R axis. It's right. It's like being having a vector in the y direction, it has no x component. Having a vector in the r direction has no perpendicular component. So it's 0. So 9 is correct. So that tells us what about the radiation? There is none, right? Which is what we saw before with that demo. Along the line of acceleration, there is no irradiative and because there's no perpendicular component to the acceleration. Let's do one more. The quiz is short, so we can do one more. Okay, let's see if you can do sort of 2 steps in one. Okay, just figure out the direction of a perpendicular at location S given this direction of acceleration. Okay, 8 is correct. 8 is correct because you draw an r vector, right, that points to S. That's r. The perpendicular axis is now this way. And we see that if I decompose this vector along these axes, that's going to be a perpendicular. So if this is a positive charge, if this is a proton, when the radiation reaches it, E radiative will be pointing in which direction? E radiative will be in what direction? 4, right? Because we have, again, a negative times a positive would give us E radiative in the opposite direction. If it were an electron accelerating instead, it would be same. It would be direction 8, okay? All right, so getting the direction is kind of the trickiest part. Once you have the direction, as usual, the magnitude's not so bad. We'll deal with that next time.